We'll be looking at an introduction to uncompressed video, audio, ancillary data over IP. And I was going to make this two separate sessions, but I realised that this, because it's actually only an overview of uncompressed video and not an in-depth training session, it was actually going to last only about 15 minutes. So there are a lot of resources out there if you want to know more in details about the spec for particularly 2110 and 2022. So, but I will give you an overview on how these are and how they pertain to the VB440. There's not an awful lot point me telling you about some aspect of the specification that the VB440 doesn't actually cover. So hopefully you see my opening slide. So a few slides and then we'll get into the live demonstration of the VB440. If any of you have ever done any 440 work with me before, it's pretty much the same presentation that I give to customers, potential customers, business partners. So it won't differ hugely from that. There have been quite a few upgrades to the VB440. So we've got some new functionality which look good. So compressed video and audio have been transported over IP for many years. We know this because we're in the business of monitoring compressed transport streams. So SMPTE 2022 1-4 lay out the specifications for transporting compressed transport stream, or a transport stream rather, over IP. There are many advantages in using IP as opposed to using things like SDI routers, ASI routers. They're all bespoke devices that are only used in the TV industry, the video industry. So using off-the-shelf components like IP routers and switches gives a great cost advantage. Flexibility is another thing. You have an SDI router or an ASI router, then it's a cumbersome beast, whereas of course we all know that IP switches are far more flexible. You can route packets between different switches and it becomes far more flexible. You can have one input and many outputs, for example. Off-the-shelf components, IP switches have been around for years. We are seeing faster and faster backbones, faster and faster switches, NICs and so on. So the ability to transport uncompressed video, audio and ancillary data becomes far more feasible in the quite recent past. And also of course the specifications, the protocols to enable us to do this have actually started to, well, they haven't started to appear, they've been around for a little while now, but they're maturing now as well. So we have, of course, the much larger bandwidths that have imposed restrictions up till now. I'm not going to go through these numbers with you. You know them as well as I do. But some of the problems with distributing, particularly contribution links and things like that, live sporting events, anything like that, are latency issues. So we need to be able to combat these latency issues. It's no good having a reliable network and a reliable transport layer if it imposes a great deal of latency and delay on live events. Network costs have come down and lack of standards until recently have also been a problem. The things like lack of standards, network costs and network capacity have, to a greater or lesser extent, been obviated now, and these are no longer barriers to being able to get sufficient bandwidth through a network. ST 2022-6, the transport of high bitrate media signals over IP networks. In other words, basically SDI over IP. And everyone knows about SDI. SDI contains the hank and the vank, everything in one frame. So the video and the audio and the ancillary data are in one frame. They're not separated. So it's just a case of packetizing this data and then using the 2022-6 standard to transport the SDI over IP. There are some issues with well, not issues exactly, but vertical blanking causes an issue that we will see in a minute on another slide when we're talking about the type of receivers and senders that are sending. So basically one multicast address is the entire signal, video, audio and ancillary data and timing information. So along came ST2110, SMPTE2110, and this proposed a new mechanism for transporting these bits of the signal, if you like, over IP, and it proposed separating them. And it's a suite of protocols. I'm not going to go through them all. The main ones that we're really interested in are 2110-20, which is an uncompressed video transport based on 2022-6. And then there's -21, which is traffic shaping and network delivery. And this becomes really important when we talk about things like the difference between hardware encoding or hardware senders and software senders. And then it also incorporates single video essence transported over multiple SD2110-20 streams. So a UHD broken down into smaller components, for example. Then we've got audio transported based on AES67 as the -30 standard, and then also AES3 as -31, and then the transportation of ancillary data as -40. It also includes PTP, which we'll look at briefly in -59. How to synchronize, because now, of course, we have video and audio and ancillary data flowing around a network completely separated. They no longer have any relationship to each other, intrinsic relationship to each other. So we need to be able to time and synchronize these streams, these individual flows, so that the video and the audio and the ancillary data are synchronized. And then there's also 22-7, which is redundant flows. So for example, if you are employing a redundant network path, then you would have your video, audio and ancillary data flows possibly flowing over two separate networks, two separate feeds over two separate networks. And this gives you the possibility of having a completely redundant path. But what this requires at the other end is that the receivers are also across both of those feeds. What you will see on our VB440 we call the primary and secondary feeds. I've heard them often referred to out in sort of production as the red and blue feeds. And these receivers need to be able to decide which of the network paths is delivering packets first, because it will always take the first packet on whichever interface the packet appears. And if a packet doesn't appear on a particular network path, then it will take the blue channel and take the packet from there. So we need to have some protocol to manage these redundant flows, and that's the -7. And we'll see that actually in action on the VB440. 2022 and 2110 both mandate the use of RTP for transport. And the main reason, well, apart from the sequence number, is the ability to timestamp a 32-bit timestamp. So this gives the possibility to perform very precise timing calculations on individual packets as they arrive. So we have video sending lots of packets, because obviously video is going to be the much higher bandwidth flow. And then we have audio sending fewer packets, and we have ancillary data, the -40, sending even fewer packets. And each of these flows is on a different multicast. So we have to have some means of being able to synchronize these together. We can't afford to lose any packets. Packet delay variation will cause latency latency, and it may even cause drop packets. So the traffic shaping -21 will dictate boundaries. So in other words, it sets limits on the jitter. And it uses this so-called leaky bucket model, which is used in many other applications. It's not new for video or ST2110. This is something that's been around in network architecture for a long time. So we get jittery packets coming into a buffer, and they will arrive with a certain amount of jitter, RTP packets closer together, further apart. And they flow into the bucket, and then they are fed out at the bottom at a predetermined rate. So no or very little jitter in the outflow. We have this Cmax, which is the maximum size of the buffer. There's a whole load of mathematics on this, and there are a number of resources and YouTube videos. If you're interested in how 21 works, Dash 21 works, there are several videos out there that explain it in greater or lesser detail, depending on how much detail you need. But the leaky bucket is measured at the sender side, and the drain rate is determined by an algorithm, and this results in well-behaved IP traffic on the outflow, and there should be no more packets in the bucket than defined by this Cmax, again defined in this algorithm. The reason I'm showing you this is because we have in the VB440 recently added these parameters. We're measuring these parameters in the VB440, and we can display them on a graph. So there are defined three different sender types. A narrow type, so we have gapped, which is the word I was struggling for earlier. SDI is what's called gapped because in the vertical blanking interval there are no packets being sent, so it becomes sending all the packets for the video and the audio and the ancillary data, and then there's a period where there are no packets being sent, and this is called gapped. Narrow senders typically are hardware-based senders, so something where timing is easy to get exactly right, and this sets a limit, a very narrow limit, on the data and how bursty this data can be for a narrow sender. Then we have the narrow linear, which is regularly spaced. So basically things like 2110 video, there are no periods. Well, there are no set periods when no video packets should be sent. So this becomes linear because the packets are all arriving one after the other, and there are no set gaps. And again, this would typically be a hardware-based sender. A camera, for example, a camera would be a camera that was outputting 211020 video would be a narrow linear sender. However, a camera that was sending SDI over IP 2022-6, then that would be a gapped sender. And then we have the type wide, type W, the wide. And this gives a broader spec. And again, if you want to know the numbers, they're very easily found. Things like software devices that are sending, that don't have the ability to precisely time and send out packets very regularly. In doing the research for this, I found out that actually software devices, server devices with particularly the interfaces, are becoming far better at sending this type of traffic and can act more and more like a narrow sender. So when you have a receiver at the other end, whether it's a receiver or anything in the network that receives these packets, they need to know the type of traffic. Session Descriptor protocol is a means of being able to automate to some extent the recognition of what some sender is actually transmitting. All of that information can be held and transmitted in a Session Descriptor protocol, and this is used by any device in the network to identify the stream that it sees and to determine whether or not it wants to join that stream because it needs to process it in some way. So it's basically a human readable text, and there's an example of a particular file there, or part of a file. Again, lots of resources out there to enable you to get to grips with STP. Now there's one particular type of STP, NMOS, and this is divided into separate protocols. You don't need to know the multicast address. Whenever a sender originates a stream, whether that's a video from a camera or some audio from an audio processor, then that announces to a central registry the stream that it's sending. And this central registry is available to any other device on the network, so including our probe. So our probe can see the registry, assuming it's set up properly, of course, and then it can then, rather than actually input a multicast address to get the video and then another one for the audio and then another one for the ancillary data, we can see the flows in the registry. And then there are tools that enable you just to click and drag and allow the VB440 to join. So if it was a vision mixing desk, for example, then the registry would allow different banks to be set up with different cameras, and that would all be done automatically. Well, semi-automatically. The ISO 4, 5 and 7 are in blue because they're the protocols that we actually support. I'm not sure about network control 8, 9, 10. I don't know whether they will come in time, but right now we support ISO 4, 5 and 7. If you just look up AMWA, the Advanced Media Workflow Association, you can see that it's very well detailed there and it's extremely readable. So where do we actually use a VB440? How is uncompressed over IP going to make an impact? Well, it's making an impact in several different ways. We can have acquisition and production, a truck, an OB truck with maybe 10 cameras going into it, remote production, and those cameras and audios and other playback devices, instant replay, all of those devices would be IP output or some mechanism of providing IP output, and then that would be mixed in the truck as normal and maybe sent to production feed also in IP. Well, the VB440 can monitor all of those uncompressed feeds prior to the head-end production process, including encoding and multiplexing and transmission, of course. But that's one model. But there's also this remote production model that is being used, particularly in Australia. Actually, Australia seem to have grasped this. They're actually doing this in a very serious way, where they have reduced crewing out at the event. So they don't have any directors, PAs, engineers, vision mixer, sound mixer, audio engineers, racks engineers. They don't do any of that in the production track anymore. That is all done at a central location. So you can see that there are major cost advantages here. You're not sending a whole load of very expensive people out to a remote production site, including hotels, transportation, and all of that. And all of the production decisions are made centrally. Again, the VB440 can analyze at the acquisition site, and it can also monitor at the central production site. But because the VB440 is a web-based device, it can be situated in either of these places or both, but it can be web browsed by anyone on the network. So you may have your VB440 in the truck, analysing all the camera feeds, analysing audio feeds and so on. But the people who are actually looking at it, who are actually using it to monitor, are still centrally based. So it becomes a very flexible tool, and one of the tools that will enable this remote production type of working. That will inevitably increase in its usage. So the VB440 comes with dual 100 gig interfaces, but they are not currently used up to 100 gig. So we can use them 40 gig, and we can add an additional 40 gig to get 80 gig currently. It supports 2022 redundancy monitoring, It's based on a off-the-shelf server, so it's not available as a software probe. It's only available as an appliance. So basically we supply the appliance, the server, everything is there. The application is already loaded onto the server, and it basically switches on, and there it is. I've done demos at customer sites, and we've had it running within half an hour of power on. It really is quite simple to set up. It's now, as of about a week ago, 2 weeks ago, it's now compatible with the Video Bridge Controller, the VBC. So this means that the VBC can be monitoring a complete monitoring system, uncompressed on one side, and the compressed monitoring system, the compressed production system on the other side. So a complete monitoring system now. The VB440 can support up to 8 simultaneous users. We call them instrument view engines. 8 simultaneous users. I think it comes standard with 2, and then you add others as a license. ST2022-6, 20, 21, 30 and 40 for 2110, AES67. We support NMOS, as I said. Ptp 2059. We can capture PCAP recordings of individual flows or entire streams. We now support SCT104, which is the uncompressed version of SCT35. In other words, events that are entered to trigger some downstream device, typically an add insertion or some regional opt-out, something like that. Okay, so the first thing you notice, if you haven't seen a VB440 before, and you can, by the way, you can go and look at our VB440 here. It's available. I'll give you the username and password at the end. So this is one instrument view. I am now logged into the VB440, and I am one instrument view. Or what I didn't tell you is this instrument view is also available as a hardware option. We can supply touch panels in, I think it's a 4RU 19.5-inch rack unit. So it's a touch display, so basically sitting in a rack, or it can sit on a desk in an aluminium mount, and it can even go in a VESA mount. So basically it's a touch panel. Everything that you see here, you can see exactly the same on a touch panel. Touch panel just gives you that immediacy of a touch panel without the need for a keyboard or a mouse, and that counts as an instrument view as well. So you have 8 instrument views, and that could be 4 touch panels and 4 web browsers, or 2 touch panels and 6 web browsers, however you want to cast it. I'm going to dive in and show you the monitoring display that an engineer would be using in a truck, an OB truck, or back at central production hub. So we have several streams. Now remember, at the very beginning I said some of these streams aren't working because we had heating issues. I think it must have got very hot in Oslo yesterday. We've got several streams. Now these streams are mainly 2110 streams, consisting of 1 or more flows, but we do have 1 SDI stream, so basically this single multicast with everything in it. So if we click on that, I can show you video. I'm going to make that slightly bigger so that it actually appears a bit better. So the first thing you notice is we've got live video, and we've also got burnt-in timecode. That burnt-in timecode is coming from the ancillary data, which is part of this stream. The video is, I can make, first of all, I can make this a full screen if I want to. So if I were on a small monitor in a truck or something, I could make it bigger so I can make sure that I'm seeing the right pictures that I was expecting. You also notice there's a closed caption button here. Now there aren't any closed captions on here, but I could turn closed captions on and off and display them were they to be in this particular stream. You can see we've got audio bars going up and down, live audio, stereo pair. you can see that we are seeing SDI over IP at 1080p 5994. The audio is 16 channel, 48 kilohertz, and the ancillary data is of course SDI over IP as well. Now I'm going to come back because I want to show you this in more detail when I show you the 2110 flows, because we've got a whole load of we've got network, packet flow, video and audio, so we'll come back to those in a minute. Also, we have access to the individual streams down here at the bottom. Remember, you know, you can imagine this being a touch screen. I mean, it could actually be a touch screen, a proper PC with a touch screen, you know, a Microsoft Surface or something like that. So, and you could touch those. Now, I can't remember which ones work. I know MGP27 has stopped, but I'm going to show you this because although the video's not working, the rest is. So I can actually show you how this works. You can see the time code, the burnt-in time code is actually incrementing, so that is working up to a point. It loops around very quickly. So this is a stream, MGP2017, so that's the stream name, and inside that stream I've got multiple flows. I've got, if you look over on the right, to the right of the picture, I've got video primary, video secondary, I've got audio primary, audio secondary, and I've got this SCT104 trigger points or trigger events in the stream as well. So I've got a primary and a secondary video, and I've got a primary and a secondary audio. So these would, in a production sense, be going between on different networks. I can switch between the primary and secondary here. Now, if my playout servers hadn't stopped running, I would be able to see this moving video. So we're not seeing any audio or video, unfortunately. But it's telling me that my video is 1080p 50, 2 channels of audio and ancillary data. Little green bulbs telling me that they're all active. And again, I can make this larger if I want to. It's really frustrating because this was working earlier yesterday. So the status is showing us. Now, if you're familiar with BridgeTex probes, you'll remember the media window. The media window shows us above the line, it shows us IP jitter, and below the line, it shows dropped packets. Of course, in the compressed world, it's showing us dropped transport string packets. But remember, this is our RTP. Everything is RTP. So we're seeing dropped RTP packets on these displays. So there's some summary information, video, number of errors since this has been running. It's telling us the sampling, 422 10-bit, bit rate, 2.18 gigabits. So there's a whole load of information on the individual flows. And this little graph here showing us our jitter in light green, and below in dark green, drop packets. If you look at the secondary video, you can see, if you look at the secondary video, you can see that we're getting continuous errors. Each of these little red excursions on the graph indicates dropped RTP packets. And it's telling me that I am currently in error. A lot of errors, you can see them going up. So nearly 1 million errors. So if we wanted to see this in more detail, we'd go to the network. Now the network just brings those 5 flows onto one screen and allows me to actually see them in more detail. So I can click on the secondary video, which is the one with all the errors, and I can see this in more detail. You can see we've got a bit of jitter here actually, not a great deal, but we are seeing jitter. And we are seeing continuous dropped RTP packets. Now if you look below that, we've got this packet into arrival time. The packet into arrival time is like, well, basically it's a histogram. It's a histogram shown in real time. So the brighter the line, or the brighter the point on that histogram, the greater the number of IP, RTP packets that are arriving at that time. So by looking at this graph, I can see that the majority of my RTP packets are arriving about 3.5, 3.8 microseconds. Then I've got another peak about 4.5 microseconds. So I can see that although I'm getting a lot of errors, I am basically got quite a reasonably well behaved stream of packets. If we look at the primary video, I'm going to close that one and open the primary video. You can see we've actually got a greater spread on this one. Again, we've still got the majority of our packets arriving about 3.5 microseconds, but we have a greater spread up to about 12 microseconds. And there's a lot more detail. So we've had the signal for 3 days. We've lost 149,000 packets in that 3 days. Number of errors, 476, and packet loss 476. So all of our errors have been packet loss. And then it's got some other information, the source MAC address, the IP source address, inter arrival time average, minimum, maximum, average bit rate, minimum bit rate, maximum bit rate, and so on. And we can do this for all of the streams. So if I wanted to look at the audio stream, again, much more detail on the audio stream. So that's the flows sub-display. Then we've got the capture display. And now this is where we can make a PCAP. So if you've ever used Wireshark, then you'll know what a PCAP file is. It's basically the IP packets. So we can select the entire flow. So we collect all of the flows and we make a capture of all of the flows, including the SCT104. And we just make one big PCAP file with all of those flows. Or we can say we're only interested in the secondary video because after all, that's the one that's giving us the problems. We're getting all the errors on the Matrox 2 video at secondary. So maybe that's the one I want to make a capture of. And I can just capture that and I'll make a capture. So there we have my Matrox 2 video, and I can just download that by clicking on the PCAP, and that will actually download to my local PC. So that gives you the ability to do some quite deep diagnostics here. Also, it's also useful if customers are having issues and you need to send a PCAP back to us. Again, that's a really useful diagnostic tool for us. And then we have the other subsection, timing. Now this gives us several graphs. It looks quite complicated. We can set the range of the graph over 5 minutes or 30 seconds. Now, the first graph that we see is the path delay. And the path delay is using this RTP timing where the sender timestamps the packet as it sends the packet out. And then we read that timestamp and compare it to the time now in the interface. So when we measure path delay, we're basically saying how long it's taken for the packet to get from the sender to us as a receiver. Now, normally in a well-behaved network where everything's working fine, this would be a straight line. It wouldn't be changing much. Now you can see that the path delay on this, and we can turn these off. So we can turn off the video and the audio and just see the path delay for the ancillary data. And the ancillary data is, the path delay is changing. It's going down and down and down. The path delay is getting greater and greater and greater, and suddenly it goes back up and then comes down again. So there's something wrong with this feed. If we wanted to look at the path delay for just one of the videos secondary, which is giving us the problem, that looks okay. We can overlay primary and they're basically the same. So there are no differences in the path delay for the video. That's a nice straight line. That's exactly what I was expect to see. Now we've got some other graphs. We've got the first packet arrival time. So this gives us the average, the minimum and the maximum for the first packet. And then I'm not entirely sure what first packet time margin is, but I guess we'd be looking for gross changes in those. Remember, we can change between, when we're looking at the path delay, we can change between 30 and, actually that's, yeah, 30 seconds. That disappears off the top. So 30 seconds, you can see it's far more dynamic when we're looking at 30 seconds. Then we've got the virtual receiver. So we're actually looking as though we're a virtual receiver. So when we looked at these narrow and wide receivers, this is where we're making some calculations as to whether we're fit into the narrow or the wide receiver. So we can actually determine whether our sender is a wide or a narrow sender by looking at this graph. Virtual receiver underflow and overflow. In other words, too many packets, too few packets. And then we look at the maximum, the overflow. So we look at the C max, C average and C max. Remember, that's the leaky bucket model, the maximum. So we're measuring that for all of our individual flows. So this is giving us a visual display of network burstiness. We go back to 5 minutes. I don't know where it's, well, not much, 3 microseconds. So again, engineers would be looking at this, network engineers, production engineers would be looking at this to make sure that everything was behaving correctly. These are the tools that an engineer needs to be able to use. Something I didn't tell you about, the widgets, as well as being able to see these instrument views, in other words, see all these graphs and show live video, audio bars, and some other video tools that I'll show you in a minute. Widgets allow users to extract from the VB440 individual components of these displays. So graphs, video, all of these sort of things can be actually extracted away from the video, the VB440, and formatted into a customer's own web page. So you could quite, say you had a 6-camera, say you had a 6-camera shoot, and your VB440 was across those 6 cameras. Remember, we're not limited to multicasts or camera flows or audio flows. We're only limited by the interface speed. That's the limiting factor, not something like a Prism, for example. It can only actually look at one flow at any one time. We can actually look at multiple flows continuously. So those components can be, so those 6 cameras, the videos from each of those 6 cameras, and maybe the graph, and maybe something like the Waveform Monitor, can be extracted from the VB440 and displayed in a web page on a user's own design of web page. So that again makes the VB440 supremely flexible. Okay, well, I've had enough of that for now. So let's go to packet flow. So when we talked about ST 2022-7, this redundant packet flow or redundant network paths, then we need to be able to establish which of the network paths is ahead and by how much. And this is laid down, this is defined in 22-7. So you can see that we have, for our video, you can see that we're receiving a primary video and a secondary video. Well, that may be a red video and a blue video. And we are timing those packets coming into the interface. And we're establishing which one arrives first. And also whether we lose any. Now we know we're losing packets. We can see them on the right hand graph. We can see those packet losses on the left hand side of that graph as it goes downwards. But we remain protected because those packets are arriving in the primary flow. So you can see that when we look at our primary, our receiver, and we're looking as though we were a receiver, is receiving 100% of our packets from the primary network path. If you look on the secondary, you can just occasionally 1 packet, 3, 4, 5 packets, you can see those packets arriving. So they would momentarily arrive on the secondary path, in which case any receiver, any actual receiver that was doing some work would actually take those packets first. But we can see that we are protected within the meaning of 22-7. because these flows are about, well, you can see the path differential here, about 2 to 3 microseconds differential. So that will show you the maximum. Now there becomes a point, of course, where if the secondary falls behind the primary by enough, then it won't be able to recover, because you won't be able to, if a packet gets dropped on the primary, it won't be able to get that packet in time from the secondary. So this graph's really important for showing your network integrity and your redundant integrity. You can look at the audio in the same way. Well, we don't have redundant flows for the SCT104. So this is basically just a meaningless. Well, it's not meaningless, but it's actually showing you the entire flow, not 2 flows. Okay, so video, we do have a few video tools. We have a Waveform Monitor, so we've got luminance and chrominance there. We also have our Rgb Parade, so we can see our Rgb Parade. Now these are the sort of graphs that can be abstracted from the VB440 as a widget and shown maybe underneath the live video. So we might have the live video above from each camera, and then we might show the Rgb Parade. So we also have a vector scope, and if you're doing lineup with your 100% bars or your 70% bars, then you could do your lineup here depending on your color space. And we even have a diamond display as well. Okay, so audio, we got no audio. Let me go back to the SDI and show the audio. So you can see we had 16 channels, but we're only using 2 of them. If I unmute them, I think you might be able to hear the audio. Not much going on there, just some sound effects. But I could switch between my audio channels, and I could monitor all of my channels individually if I wanted to. Then I can mute them, and then it gives you just a bit more information about the audio down below. Ancillary data, well, this is the ancillary data that we're seeing on this particular SDI feed, of course, and it gives you the number of packets and the number of words and some information about payload identification codes, time codes, and audio control. Is there any, have we got anything with ancillary data? Okay, so that's what's in the ancillary data for the -40. We've got AFD and bar data, payload identification code. So this is where our closed captioning would also be, and any other ancillary data that was being carried. That is the overview. That's the engineer's view, the technician's view, the production engineer. Now we've got a couple of other displays I'm going to go through really quickly, no more than 10 minutes. So we have a list of every individual flow. You can see we've got lots of loss of signals down here. So we are losing a lot of our signals, but this would show the individual flows. So if I wanted to look at the video, there it is. 31 streams, 20 monitored, 17 video, 10 audio, 4 ancillary data. Just an overview of the individual flows. Then we've got some information about the network status, if you like. So first of all, we've got the 4 network interfaces that are in the server itself. We've got 2 management interfaces, which are 1 gig, and we've got 2 data interfaces. And one of those is active, the other one is not, is actually not connected and disabled. So it's a 100 gig interface, and we're seeing about 12 gigs. So we're not seeing an awful lot. Mainly that's because of the video that's not working. And if we wanted some details on that particular network interface, then there's a whole load of information there. We're also looking at 1 PTP clock. If there were any boundary clocks, that they would appear here. We would see difference between the master clock and any other clocks that we were seeing. We'd be able to see whether they were synchronized or non-synchronized. And then any web browsers that happen to be looking at any of the live video, then you see down here. You're only going to see a maximum of 8. So we're seeing 4 at the moment. And 4 of those, it tells you what they are. So we've got a Chrome, 2 Safaris and Firefox. And the operating system that's actually behind those web browsers. And you can see details about the web browsers there. And that again, there's not much going on there, but that would graph traffic to those web browsers. And then lastly, now all of you who know Bridge Tech will immediately recognize this. This is what we call in the VB440 the expert interface. It's the standard web browser interface for all of our other probes, and it gives the user the ability to do 2 things. First of all, we can configure the probe manually. So things like if you want to set up the IP addresses of the units, this is all locked out by password. I'm not going to go into it, but this allows you to change the IP addresses of the interfaces exactly the same way as you would see in a standard probe, the ability to the data interfaces and the management interfaces, for example. If you're monitoring Ptp, which you almost certainly will be, this is where you would configure Ptp monitoring for your 2 data interfaces. Remember, we've only got 1 active. Set up your Ptp there. The NMOS is here. So again, if you're running NMOS and you want to attach to a registry, then this is where the details of the registry would be entered. And were we actually seeing the NMOS connections to a registry, then they would appear here. 1 or more registries in the system. There would typically be more than 1. And then, of course, we have the media window. So whereas we were seeing the video and audio flows, the multicasts, over a period of a couple of minutes, this reverts to the standard IP probe of 4 days. So we can, even though you can't see it on the standard engineering interface or the user interface, we can still log drop packets and jitter going back 4 days. And this, of course, would be imported into the VBC if this were attached to a VBC. Of course, everything's going to be RTP. So if we want to look at something, I don't know, then we would see RTP packets here. Multicast, we can join streams manually. Now, of course, we don't have any NMOS connections. There's no registry in our system. We don't have an NMOS system. We can't use that in order to join streams. But we do, of course, still have a manual process for joining streams. And it's exactly the same as a standard IP probe. You join the streams by adding the multicast. There's one difference, and it's a significant difference because we have flows in ST2110. We have these flows. So a stream of one particular TV channel is made up of audio, video, and ancillary. So we have to group these together to make one stream. And this is how it's done. It's done quite simply, actually. We have a name. So we give the flow a name. So this is the multicast address for the video. Let's find a video flow. That's the multicast address for the video flow. And there is the flow name. And you can see we differentiate primary and secondary with an at primary and at secondary. So if you wanted to call them red and blue, then you would just say at red, at blue. And then we group, and this group name is the name that brings them all together. And it's as simple as that. And then you tell it the join interface. We've only got one working interface, so even our primary and secondary are all coming in on the primary interface. If you need to select the type of uncompressed stream, you can either do an auto detect or you can specify it there. That's really it. That is really the VB440. So I think I'm going to stop at that point. And thank you for joining me today at this quick look at uncompressed video over IP and the Bridge Technologies VB440. Don't forget to look at the quiz to test your understanding of this module. Thanks again.